Last time we talked about the J testing of the metals, and I give you a very, very important procedure on how to determine the JQ from the JR curve. So from that, the procedure, you guys need to know and how to this is calculate, this is the J. And we have talked about several steps. And as I said in our final exam, I might ask you guys to do these things to tell me what you have learned if you are given a hypothetical, the new material. So this is the we are going to do that, and we might do that, okay, in the final exam. And today we continue our talk and to talk about the JR curve and how to calculate, how to experimentally obtain the JR curve. So this JR curve, there are several ways. We talk about this one. These means, and we have talked about these means very, very briefly. And at the very beginning of this is chapter 7, when we talk about what kind of equipment devices and we will be needing. And here we are going to talk about for this specific problem and this JR curve testing and how can we use these methods we just talked about to get this JR curve. Right, so the resistance curve test method. Here is a typo. Okay, I'm sorry. It should be ASTM. So not ASME. If you have this handout, you can change ASTM. ASTME 8020 requires that the crack growth be monitored through the test. You need to continuously monitor the crack growth. So this one is give us the disadvantage. The disadvantage is that so we need to have additional instrument, additional device, and to measure this equipment, measure this crack growth continuously, right? So this is definitely, so this one we need to spend more money to buy this additional instrumentation. And so, however, the advantage is, so this compilation is more than offset by the fact that the JR curve can be obtained from a single of the specimen. So we can just, if for this one, we can, because we have additional equipment, and we can use this additional equipment or devices continuously to check the crack length. So that means we can use a single specimen, right? For a single specimen, we apply load continuously, and as the time goes, we can measure the crack growth continuously. Single specimen can save us a lot of money also. Please note that determining the JR curve with a basic method requires tests on multiple specimen. We talk about the basic method. Basic method means we have multiple specimens. Each specimen we just fracture, let the crack grow. For each fracture, for each specimen, we have different the crack growth, the crack length. For each crack length, and we measure for each of these specimens, and we measure, and this is our curve. So then we put everything together. And as I said, if we are using the multiple specimens, you know, the multiple specimens definitely will cost us a lot of money. So you need to know that, okay? So so whenever we do something, and sometimes we have advantages, and sometimes, and also we have some disadvantages. And whether we select this method is dependent upon which one is our advantage. Other advantages and outweighing is the disadvantage or vice versa. So you need to be very, very careful. So there are several ways for single specimen test technique, and we have 3 single specimen test techniques. And I might ask you guys, okay? And in our final exam, because here we are talking about some concepts, some conceptual knowledge. And so if I give you a short question you should be able to answer. For example, what are the commonly used three single specimen test the techniques? And you need to know that for this JR testing, and you can come to these slides to get the results. So these are our first one, okay? Our first is unloading compliance method, or you can just call this a compliance method. And as I said, compliance is a reciprocal of the stiffness, right? If we say this material is more compliant, it means that it is less stiff, less stable. If we say this material is stiffer, and we say this one is less compliant. So be very careful. This is a load, and this is the displacement. Load and displacement, and you can see this is the short lines. Means this is unloading, okay? And we go here, and so for example, this is the displacement, and so this is load, and at the very beginning, almost very straight. At some point, the material used, and then we have straight hardening, and then at some time, and after we get here, and we just remove the load. This partially unloading. Okay, so if we totally remove the load, it will come to this is the x-axis. You should know that, okay? So this one, this is go here, so that is partially unloading. As is fully unloading means that so this curve, this straight line will go all the way down to intersect with this x-axis. You understand? Partially loading. So this short line is partially unloading. Partially unloading, and then you can see. So here, this guy has a slope, and then we just load back. We just load, and then go further, and we will do it again. Unloading, partially unloading, and we will see that. So this slope and this slope, they are different. Okay, why they are different? Why they are different? Because the crack grows, right? For the specimen, either the compact the specimen or this is the single-edged notch specimen. We know that if we apply load, if the crack becomes bigger, and this is the material, this specimen becomes softer. That means becomes more compliant, right? So we know that, and as this crack grows, and so this guy's slope will be less than this one. That means this guy is softer, and so this guy is less stiffer with this than this. And so as I said, C is the C is the reciprocal of this is stiffness, and so that means compliance it becomes bigger. Compliance of this one becomes bigger and bigger and bigger. And so we know that. And we go this one all the way down. So this is ultimate strength. And then we go here. You can see we have this is many partial loading, partial unloading, and then reloading. This is the trajectories. So based on these lines, this is the screen, this data, and we can calculate the C, right? Because we know this is the stiffness, the slope is the stiffness, and compliance is the reciprocal of the stiffness. So this is the first method. You should know that, okay? So the crack length is computed at a regular interval and during the test by partially unloading, and you should have regular intervals. For example, every 3 minutes, I will check the new crack length. I just give you an example. It depends on how stiff your material is. During the test by partially unloading the specimen and measuring the compliance. So as the crack grows, okay, we know that specimen becomes more compliant. That means less stiff, and the various J, okay, the various J testing standards provide polynomial expression and relating A over W and to compliance. And we talked about this one before. So this J is a function, polynomial function in terms of A over W. So the ASTM standard requires a relatively deep crack. Why? Because the unloading compliance technique is less sensitive if A over W is less than 0.5. So this is understandable, right, guys? Do you guys agree? At the very beginning, for the specimen, suppose at the very beginning there is no crack. At the very beginning, the crack grows very slowly, and then the C here will be changing very slowly. At the very beginning, you even cannot, within, if you are using the some instrumentation, some device, and your device might not be able to detect the difference between the C's at the very beginning. This is understandable, right? However, if the crack grows bigger, and crack grows bigger, and we can very easily see the difference of the compliance for different, this is a crack length. So this is the first technique, unloading compliance method. If I ask you guys to draw the diagram, that means I want this figure, okay? Don't be confused. Next one is a potential drop procedure, and we learned this one and a couple or maybe 1 week ago, and the day before, and I also talk about this one to show you to refresh your memory about this is the potential drop procedure, and it also using the principle that if the crack grows and the resistance, electrical resistance of this is a specimen will become bigger, right? It will become bigger, and we know that this voltage does not change. Voltage is fixed, and we will know that from here to here, this voltage drop will become bigger. You understand, guys? So that is a physical principle for this device. And based on the change of voltage, you can know how big the crack is. And how to do that, guys? If you have never designed, and built and tested, this is the sensors, and you should know that you need to calibrate. Okay, guys? You understand that? You understand? So, for example, the voltage drop, how the voltage drop corresponds to the crack growth, and you need to know that. However, when you buy this device, commercial device, from some vendors on the data sheet, so that relationship will be given. Okay? How the voltage drop corresponds to the crack growth. That kind of the data is given. However, if you are designing this one, building, testing this one by yourself, you need to do the calibration. Do the calibration means that you need to generate a data sheet and to correspond the voltage drop to the crack growth. Understand? However, but if you buy this one from this vendor commercially, and you can just get the data sheet and can save you a lot of time, but you need to pay more money, right? You understand, guys? So this is our second. The technique, and you can see as the crack grows, the V is high. Why? As the crack grows, so this is the electrical, the resistance, from this point to this point is high. Why? Because as the crack grows, and so the electrons will have less this surface to pass through. Right? Even though, guys, you can see, even though we have a very sharp is a crack, but basically from this is the bottom surface and that's the top surface, and they are electrically isolated. You should know that, okay? You should know that. So the third technique is normalization, and it says that it uses infers the crack growth from load displacement curve and load displacement curve here. A specimen in which the crack is growing and goes through a max load plateau and followed by a decreasing in load, but the load displacement curve would continuously rise in the absence of crack growth. Right? The normalization method is particularly useful for high loading rates and where techniques such as unloading compliance are not possible. So this one is so there is a Maxim, right? Maxim is doing the simulation research with me, machining research with me, and for the machining, when we machine some materials, and we have very, very high loading rates. Do you guys agree? Do you guys have the experience of operating any machines in the downstairs machine shop? So when you machine something, that is kind of loading rate is very, very high. Strain rate is very high. So for that one, and when you want to do that kind of loading the rates, especially when you get the Johnson-Cook the parameters, and you are supposed to use this method, these techniques. Any questions regarding these three the techniques? Okay, I will ask you guys and to what techniques we have talked about for the JR testing and what they are and how they work. Then we talk about the specimen. Okay, the specimen should be set grooved and to avoid shear leaves and this crack tunneling. And okay, and I might ask you what are the benefits and for us to set a groove, and this is the specimen before we use it, and to avoid shear leaves and crack tunneling, and proper set grooving, and will also produce relatively uniform the dartle crack extension along the crack front. So pay attention to this statement. So the 27, okay, so you can see this is the lecture 27. So the ASTM procedure for JR curve testing and utilizes the deformation theory and definition of J. Okay, what is it? And which corresponds to the rate of energy dissipation by growing crack. And this is energy release rate. So figure 3.32 and contrast the actual loading paths and with the deformation paths. So this is actual loading paths. So this is a deformation path. Or this is the deformation path. Okay, this is the deformation path. So the deformation J is related to the area under the load displacement curve for stationary crack. That means the crack does not change. Rather than the area under the actual load displacement curve, where the crack length is varying. So here for this one, and so this crack does not change. For this one, is the crack growth is changing. How can I know for this curve the crack growth is changing, crack length is changing? Because you can see this is these lines and they are unloading lines. Okay, so this unloading, this is the slopes and they are decreasing. That means compliance is becoming bigger and bigger. Since the crack length the changes continuously during the JR curve test, we know that, okay? So continue for single specimen. The J integral must be calculated incrementally because it's changing length. For unloading compliance test, most logical time to update the J value is at unloading point where the crack length is also updated. So you can see for each of these points, and we have different crack lengths. So for a given measuring point on this actual loading path, and we have I, okay? I means the iteration, so the point. Suppose we have multiple points here. I from 1 and to lowercase n. And we have many to this measuring point. So the elastic and the plastic components of J at that point, for that point only, that point means corresponds to a fixed crack length, can be estimated by this figure 726. And figure 27.6 is this. The figure 26. Right? Suppose this is AI, you have this curve, and this is AI minus 1, you have this curve. So you can see the J elastic for I iteration, for I point, and it equals K square, and I for I iteration, I step, 1 minus nu square E. So this is the, keep in mind, so this is plane string condition. So this means is a thick plate. Okay? Whenever we do the experiments, we are supposed to use thick plates instead of thin plates. So this is a 7.15a. As we get this elastic I, we can calculate the plastic I based on the history, because the I minus 1 is for the previous step, for the previous point. And we have, this is the previous step, JPL, and this is the previous step. Bn, we know that Bn is the net thickness of the specimen. B is the ligament length, I minus 1, means the I minus 1 step. Eta is the constant, and E, I minus 1 is also the eta value and at the I minus 1 the step. And for this one, Pi is the loading, okay, because the loading is changed at this I step. Pi I minus 1 is the loading at I minus 1 step, and delta I and delta I minus 1, and they are the displacement at the I step and I minus step. This is respectively. So PL, and PL means that it's only because of the plastic deformation. And so here we multiply by the square brackets 1 minus nu minus 1. AI is the crack length at this current, the I step. I minus 1 is the crack length at the previous step, I minus 1. And B, I minus 1 is the ligament length at previous step. So, and here I'll give you all the details here. So, delta I PL is the plastic load line displacement. The gamma I here equals 1.0, and for single edge, this is the specimen. But for gamma I equals this, and for the compact the specimen. So I just for compact specimen. For the eta, also for two different specimens, and the eta values are different also. Single edged notch, the bending specimen. So this is compact. So this is for the compact one, right? I need to write down for compact one. So BI here, and BI is the instantaneous the ligament. I keep in mind the B is the ligament length. BI is the instantaneous ligament length at this iteration, at this step. So Ki, right? So this is Ki, and Ki, okay, this is the instantaneous K. Now this Ki equals Pi, the current loading condition load, and the square of the B is the gross, the thickness, and Bn is the net thickness. Net thickness means that you measure Bn at the point where you set a groove, right? So Bn. So F is a polynomial function and in terms of A divided by W. Here is the AI, okay, because the AI is changing, A is changing. And for this iteration, this step, we focus on AI. However, the W is a constant. W does not change, and when the query length is changing. So here, keep in mind, here is the AI here. So PI is instantaneous. The PA is instantaneous A. So ASTM 1820 E1820 has the following limits on J and crack extension relative to a specimen set. That means the B value, the thickness value, and also B0, and B0 is initial ligament length. So these two guys must be equal or greater than and 20 multiplied by J maximum and divided by sigma Y. Let me ask you guys, the sigma Y is our old friend, and can somebody tell me what the sigma Y is? Can somebody tell me what the sigma Y is?
Is it the yield stress?
No, last time we talked about this one. Last time we talked about this. Can you check the previous lecture, guys? And then tell me. I'll give you 3 minutes to check. And sigma Y, this is very, very important one, okay? And check the previous one. And in previous lecture, I talked this B sigma Y in detail. And what is the sigma Y here? Yield strength, we use sigma Y YS. But here, we use sigma Y. What is the sigma Y? And after 2 minutes, I'm going to cold call someone if there is no volunteer. Let me check, okay? All you guys check, and then I will cold call if there is no volunteer. One more minute. Okay, guys, and who can tell me what the sigma Y is? I hope.
The flow stress.
Flow stress? Great. And how can we derive this flow stress?
There's an equation here. The half yield strength plus TS.
What is the UTS? Sigma UTS. What is the sigma UTS? Yeah. Sigma YS is the yield strength, and sigma UTS is the ultimate strength. Ultimate strength is the highest point of this is the load and the stress strain curve. Be very, very careful, okay? This is very, very misleading. You can see this is our first requirement, and we must be satisfied. Another requirement is that the delta A maximum cannot be greater than one quarter of B0, right? So be very, very careful about this. Otherwise, for this curve, okay, for this is the diagram, and shows that a typical TR curve from here and going up,
and within the ASTM valid limit, you can see, so this is delta A maximum, G maximum. So this is the limit. Outside this limit, and so the GR curve is considered invalid. That means from here to here, they are considered invalid. That means we can only use the data points and within this is a rectangular shape. Any questions so far?
Is B0 just the initial ligament length?
B0?
Yeah.
Yeah, B0 is initial ligament length. Right? B0 equals W minus the A0. Yeah, B here in this context, B is a ligament length. B0 means the initial ligament length because the crack is growing, right? Crack is growing means that the B is changing. B0 and the B1, B2, and so on and so forth until we have Bn, that is the last step, the ligament length for the last step. Any questions you guys might have for me? Any question? If I give you hypothetical material, and can you just give me a feasible the plan and how to determine the J and how to determine the JR curve? Can you do that, guys? Okay, and then I will give you in the final exam. I might, okay, just I say I might give you a hypothetical material, and I just come up with some ideas about this. I just brag. This material is very, very nice, and the strengths, what is strengths, what is the toughness, and then I want you guys to tell me, because I'm very, very concerned about the toughness. Toughness here is a J value or K value, and how you can just do this kind of experiments for me. Right? And then at the very, very end, and don't forget to do the testing, the validity testing. That means, so these equations, these inequalities must be satisfied. Okay, guys, this is pretty much what I have for today, and this in this lecture, and several things I want to cover. Okay, so this is how many what are the single specimen test techniques we have talked about to measure the JR curve? And 3. And what they are, you need to tell me. So these are results here, right? And then if I use this is the actual loading path, and what are these equations, and then finally, and how to check the validity of your results using these two inequality. So this is very, very important, guys. Even though I do not ask you to memorize all these equations, however, when there is a need that you do something and to determine the J value or the K value, and using the experiments, you can just come back here to check the procedures I just talked about. Okay? And what questions do you have before I end today's session? No question? If there's no question, I'm going to end today's session, and I will see you. This is the upcoming Monday. But Wednesday we do not have class, right? Next Wednesday.
Wednesday and Friday.